All right, so again, hi everyone. So this is our class number 4 in terms of the syllabus. We want to talk about something that appears also in the first assignment, and this is the Griffith-Lim. That's the second part. But before that, I would like to talk a little bit about how to invert and perfect reconstruction, conditions for inverting short-time Fourier analysis back to the signal, which is an important theoretical concept. It actually is the basis for a lot of later on manipulations of sound, like time stretching, pitch shifting, basically changing the duration of the sound without changing the pitch, or changing the pitch without changing the duration of the sound, which are operations that are normally done in the frequency domain. So let's talk a little bit about that. As we have seen already, the idea that we process the sound by taking a waveform and we multiply this by windows. It's like a window or something which is tapered. We'll talk just a little bit about what are the windows and what are the conditions. Once we move this window with certain skips, a certain hop size, so I mean that's the usual term, then we have an ability to extract an FFT or do a frequency analysis at around this time moment. So one way to think about this is basically as doing a sequence of Fourier analysis on different signals, and we index these signals with an M here. So this is signal 0, signal 1, signal 2, which are basically the original signal multiplied by this window W, which is shifted at a step of size R. So we have a frame step of size R, and we index these gaps. So we have at 0, and then at R, and then 2R, and so on. So we have seen that in spectrogram analysis, of course. So once we do that, we take each window, we process this by a short-time Fourier transform, or basically we process this by a DFT. Sorry, I'll have to change here. It's a DFT, not DTF. So we have a discrete Fourier transform. So we process every and we get a complex spectrogram or a Fourier analysis. And so the sequence of these Fourier analysis frames comprises a spectrogram, and this is a complex matrix. And you've already seen that if you started doing the assignment. Now you can invert each of the individual columns or each of the frames of the FFT to time by going through inverse Fourier transforms. So again, it's inverse DFT. Pardon me for the errors, and I'll correct the slides after we're done. So if we do that, we end up with having back the original XMs. And the most simple way to reconstruct the original signal XM is sum them back, right? So just kind of reminding ourselves what XM is. XM is the original signal multiplied by the window. So since we're summing on all possible shifts, the M is the index of the shift, and not on N, we basically can take, it's just kind of a mathematical proof. We can move the Xn out of the sum, and we get the sum of the windows. So here it's evident that in order to reconstruct Xn, this has to be 1. So this is really the condition called constant overlap add condition. And I didn't mention the overlap add, but it was I think in the title here, overlap add short time Fourier transform processing. So the idea that we basically overlap all the windows add to 1, trivially we have the perfect reconstruction. So, okay, let me hopefully make sure, okay, the internet I hope is still okay. And if, if anybody misses, if I'm suddenly going blank or muted, let me know once I get back so I know which section I should repeat. So hopefully we are still all on the same page. So this condition actually requires some tweaking, or at least being careful about the windows we choose. So of course, if we take a rectangular window, which means just basically box, car, another name, ones and zeros, so a segment of ones, we can shift by basically no overlap, okay? So zero overlap, this is not the hop size, it's the overlap. The hop size for 0% overlap is the full window, and that works fine. And we can, of course, overlap this more, and we'll still be okay, just that the sum might be 2 or 3, 2 or 4, so we need to normalize the value. If we take triangular windows, we do need at least to have 50% overlap. 25% overlap, and you're going to just need to make sure that the length of the window is odd, so we shift to the one after the, we shift actually to the middle, okay? So another window which is very common because it has some nice properties in terms of the frequency resolution is Hamming window. We didn't explain what it is. It's kind of a cosine shaped window, raised, sometimes they call it raised cosine. Really, this is beyond, you know, the detail of signal processing that we want to go into. But once you choose a window, you can see that it creates some sort of an effect on the spectral analysis, and smooth windows actually look better. They have so-called less side lobes and things that we didn't cover. But the idea is that really when we analyze a window, when we analyze the signal with SCFT, we analyze the window version of the signal. And if we don't have a window, which is smooth, but we have something like that square window, rectangular window, the analysis kind of includes some aspects of the window frequencies, and any abrupt thing on the window itself will affect and create so-called side lobes that will actually not frequencies created by the window and the signal. And really, if we take any window, whatever shape we want, and we move by one step, once we start integrating the windows together, we can also make sure that we normalize by whatever the the sum of the window is, and if you move by one, that will be still flat. So here are some examples of windows that look nice, but somehow are miscalculated. This one is actually correct. It's the Hanning window. So there's Hamming, there's Hanning. This example for Hanning window with double N, and this is the correct summation. But if we don't really, even though it looks good, I mean, like we think that the overlaps are okay, but it's a 40% overlap, and you naturally get these kind of wobbling amplitude going up and down. If we overlap more than 50%, so 60% here, we also get these extraneous peaks. It's true that we can always normalize if we know how this looks. If we know how the windows sum up, we can actually have slightly more general condition than equals 1 constant. We can divide by actually the shape of that window, which kind of change, or the shape of that sum of the window values as it moves through the signal. Which is one of the references. It actually shows slightly different derivation that doesn't have these strict assumptions on the windows, but I think this is the simplest way to make sure that we can actually reconstruct signal. So let's move on to the Griffith-Lim. So I will run this without a pause, and I'll take questions about both topics together. In the homework, in the assignment, you're asked to implement the Griffith-Lim phase reconstruction. So one thing to keep in mind is that everything we did before assumed that we had the phases, and then we could use the inverse DFT to recreate the signal back from the frequency. If we use an amplitude, so the title of this page is Signal Reconstruction from Amplitudes of the Spectrogram rather than the complex frequency. So if we have these, so amplitude spectrum, which is the short-term Fourier transform without the phase information, it's not invertible by just the mathematical operation itself doesn't work out. And the reason is that not knowing the correct phases of each frequency component creates discontinuities in the reconstructed waveform between. Well, what does that mean? Well, we could and then as we move across time, because we're doing short time Fourier transform, the next frame will be also reconstructed kind of arbitrarily beginning of a waveform. Because what a phase for a single FFT frame does, it actually sets your sines and cosines. And again, my internet is unstable, okay. So what it gives you, the sine and cosine aspect, it decides what kind of a complex, if you want to think about this as a complex phasor, basically where it starts, okay? And if you just decide arbitrarily on some phase, and if you, let's say, fix that phase for every short time Fourier transform, it's clear that every time you reconstruct it, you will basically recreate sine waves, of course, of different amplitudes, but they will start in a certain way. Now, if there was a sine wave that was continuing across frames, they will create these discontinuities. So this is what I meant by saying the reason for the problem is that it's not invertible, and just assigning kind of a nonsense or arbitrary phase will create discontinuities when you move from one frame to the second one. And this is why it was important to go through the previous one, the overlap add idea, because this is where the I know the phase issue kind of takes a while to wrap your head around and say, okay, is it important? Is it not important? Do we hear it? We don't hear it. But just technically here, I would say if you don't take care of the phase, you will create artifacts. You'll have audible errors because you will create chunks of waveforms which do not smoothly move from one to another. They will have kind of jumps in time. So what we need, well, we need somehow to smooth these discontinuities out, because if we say, well, we care really more about the amplitudes and the phases are just kind of want to be continuous, this is what the Griffith-Lim algorithm does. It is an iterative method for creating a continuous phase for a given desired amplitude spectrum. When we think about this as STFT, as chunks or bunch of Fourier transforms over time. And this is how it operates. So this is the explanation in words. We basically have an initial STFT matrix that is specified by the amplitudes, but we don't have the phases. So we create random phases. I mean, that's kind of the thing that I said you shouldn't do, but that's how you start the process. You assign random phases, and then you do an inverse STFT. And of course, each of the FFTs will create, each of the DFTs frames will create a new signal waveform. And we will have some output, but it will have a lot of clicks. So what you do now, you take this new waveform and you do a STFT analysis of that new signal with the errors, with the discontinuities. We'll see in a second why it makes sense. So now we have, again, a bunch of complex, we have a complex matrix, the complex spectrogram, with some phases and amplitudes. Now, because of these discontinuities, the STFT amplitudes will actually be very different from the STFT amplitudes of the original signal. So what we do, we kind of throw away the amplitudes of the STFT of that new signal, and we force or we replace them with the original desired STFT amplitude. And again, I kind of remind you what is the setup here. The setting is that you have an STFT matrix only with the amplitudes. So you keep it always with you. This is what you want to reconstruct. So now you force the new signal to have the right amplitudes, but you keep the current phases. And then you go, again, you go repeat steps 2 to 4 and replace, again, you do the STFT amplitude with the right amplitude. You invert again, you get a new waveform, you on the waveform, you do the stiffity analysis again. You again replace the amplitudes, and you keep on going through steps 2 to 4. And the interesting part about this that this procedure, there is a proof that it converges. So it will create a signal, and that signal will eventually create a smooth Fourier phase across the frames. So here's how it kind of is expressed a little bit more graphically. What we do is we have some initial or randomly generated, signal with random phases by, and let's say this is one frequency, okay? This is a specific frequency, and if you represent this in this kind of a complex plane, let's say this is the frequency plane with S, and this is kind of the amplitude of the S. This is one STFT, this is a fixed omega. So for that omega, let's say this is the amplitude that we want because this is what was given to us. I mean, again, I remind you that we start with the given amplitudes at different frequencies. So for, let's say, frequency omega, we know that the amplitude is this. It's not a unit circle, it's the value of that amplitude. But we don't know the phase. So all of these could be solutions for specific frames. So this is frame M and frequency omega. So, if we go through this process and step I, we actually created something that, because of these continuities, created a signal and specific phase. Force to be the right phase. We force it to be the right amplitude at the same phase. So angle is the phase, and the distance from the unit circle is the amplitude. So if this is what we start with at step I, we force it to be here, we reconstruct it, throws us again outside of the amplitude, the correct amplitude region, could be throwing us inside or outside. We force it again, and the proof is that these fluctuations will eventually converge to be, it can go back and forth, but it will converge to a point that will not move on the unit circle. So it's expressed here a little bit more in detail in the second slide. We said we do the same thing over and over. This is our desired Fourier transform. This is our estimated at step I. By dividing the complex by the absolute, by the amplitude, we get the phases. I will leave you with, basically reminding yourself in complex algebra why this is the phase. But what we have is we force an amplitude that we desire with the phase from the previous step, okay? And then we create this signal. Here the math is taken from the article, since everything there is done in continuous frequency. So you take this, you invert it back. This is the inverse Fourier transform, okay? And with these windows, you sum this together, okay? The math there, because it's least mean square, has this W here and the summation of W square. We didn't prove the math, but this is the step that you have to follow. So you invert this with the windows and you do some sort of a normalization here. And this becomes your next step, and you go back here and you go over and over, and this is expressed in this kind of algorithmic form as a computational sequence of steps or a graph. Now, having seen this, you probably wonder, well, where we need to use this kind of Griffith-Lim reconstruction. So this is something we didn't cover yet. This is an example of a speech-to-text system and deep learning, and state of the art. This is the initial tachytron. Now you have tachytron 2 and other models, but the point I want to show here is not the network itself, which is something we'll talk about maybe later when we start talking about how you go from text to speech. But the idea in text-to-speech systems is that you have sequence of characters, basically your text. You need to do some processing, you do some embedding, you do these kind of highway networks and the GRU here. Whatever that process is, that creates now a vector that has a sequence-to-sequence structure. It actually maps a sequence of characters to sequence of spectral frames. And this one is also a bunch of recurrent neural networks. We didn't cover them yet, but this is basically a sequence-to-sequence model with attention that maps a sequence of symbols to sequence of spectral frames, really. This is the output, and this is how we actually train it. We train it end-to-end from sequence of texts and spoken spectrograms of that text being pronounced by somebody. So, I mean, given everything so nicely, and you know this amazing, you know, black box, if you want, at this point, is trained to create eventually linear scale spectrogram. To turn this from a spectrogram to sound, we actually use Griffith-Lim. So from this whole picture, all I wanted to show is that you need this step. You can also use more advanced method like WaveNet or normalized flow, glow, so-called, wave glow methods, which might give you better quality of reconstruction because it's also trained a little bit better than just like a mathematical method of creating phases from partial information. But I mean, this is good enough. It's a fast process, and for many purposes, people just go ahead with this because the other methods are pretty notorious in terms of the training that they require. You can use maybe pre-trained methods, but so yeah. So this is where Griffith-Lim comes in, and conceptually, I mean, regardless of that specific application, text-to-speech, you can think about musical synthesis. You could use anything where you eventually either modify an existing spectrogram or you generate from scratch a spectrogram. And once you're done with whatever task you had and created something that needs to be inverted, this is your method to do simple and fast inversion. Yeah, I think this is pretty much, yeah, the end of this slide. And let me quickly stop the recording and